The magnetic field of Earth has a hole, and the hole is changing. It's not dangerous, at least NASA doesn't think it is, but it could affect satellites and other spacecraft. Is it an indication that Earth's magnetic field is about to flip? I've had a look. This week's spot of the magnetic field is called the South Atlantic Anomaly. As the name suggests, it's largely located over the South Atlantic Ocean, but also extends over parts of South America, including the eastern coasts of Brazil and Argentina. It's not a new discovery, but it was in the news recently because the hole is changing. This anomaly was first noticed in 1958, when scientists from early American satellite missions, most notably those involving the Explorer series, observed that the Van Allen radiation belts dip unusually close to Earth's surface in this area. The Van Allen belts are two donut-shaped regions of energetic charged particles, primarily electrons and protons, that are trapped by Earth's magnetic field. In latitude, they're closer to the equator than the regions where the aurora comes down, and at a really high altitude, beginning at more than 600 kilometers. NASA has kept close track of this anomaly because if the Van Allen belts move down, then satellites and also the International Space Station are exposed to higher levels of radiation. This radiation can affect both the functioning of electronic devices as well as that of humans. The magnetic field anomaly, however, doesn't affect aircraft because these fly at much lower altitudes. This hole in the magnetic field seems to be splitting apart into two distinct patches. A few years ago, scientists from NASA's Goddard Space Flight Center used data from the European Space Agency's Swarm satellite missions and the CubeSat Alphin mission to track how the hole has been developing. This is what the headlines were about. They found that the anomaly is weakening in the middle. Its main body remains centered over South America, but the other part is moving southwest towards Africa. A study from last year also showed that this magnetic anomaly now weakens the aurora in the southern hemisphere. Could this anomaly be an indicator that Earth's magnetic field is about to flip? Geological records indicate that in the past several hundred million years, Earth's magnetic field has reversed poles roughly once every 450,000 years. A similar process takes place in the Sun, but much faster. The Sun's magnetic field changes polarity on average every 11 years. The magnetic field flip on Earth seems to be a direct consequence of how our planet produces its magnetic field from hot metals sloshing around in its interior. That's what geologists say anyway. But maybe we live in a computer simulation and that's how they turn it on and off again. Whatever the reason, extrapolating from the past makes scientists think that Earth is about to have another flip of its magnetic field within the next 10,000 years or so. This may not be your idea of soon, but for geologists, this means basically coming up right now. It's a problem because the magnetic field reversal, if it were to occur, could weaken our shielding against cosmic radiation potentially for thousands of years. At the moment, however, geologists believe that the observed changes of the magnetic field anomaly are not a sign of an impending full field reversal. The leading hypothesis is currently that this hole in the magnetic field is caused by the motion of molten iron in Earth's outer core, which in this region conspires to weaken the emergence of magnetic field lines at the surface. Models suggest that this anomaly has been drifting around in the outer core for about 10 million years. It seems to be a localized feature that has no direct relation to the magnetic field flip. But the magnetic field hole is interesting because it's data for what's going on inside of our planet, and that could lead to better predictions of when the magnetic field flip might happen. It's also a reminder for how precious our planet is, because it so conveniently protects us from radiation with its magnetic field. Our little neighbor planet Mars wasn't that lucky. It lost most of its magnetic field about 4 billion years ago because its core cooled and stopped moving. Not only does this mean that the radiation exposure on Mars's surface is unhealthy, but it's probably also the reason why Mars lost its atmosphere. It was ripped away by the solar wind because no magnetic field could deflect it. Another explanation for the magnetic field hole is that aliens are building a portal through which they'll soon be taking over our planet. I can't wait. We just had another crazy week in AI development. Musk released Grok 3, Google released the AI co-scientist, we hear that OpenAI's GPT-5 is probably coming up soon, and Microsoft has found that AI makes us stupid. I have a summary. On February 18th, Elon Musk's AI venture xAI unleashed its latest model Grok 3. Musk himself built it as scary smart.
In fact, at times I think Grok 3 is kind of scary smart. You're like, wow, this thing's smart.
One of the first Grok queries that Musk shared was the request to come up with 3 new ideas for the nature of gravity and the unification of the forces. Grok suggested, for example, that gravity might not be a force in the traditional sense, but a macroscopic shadow of quantum entanglement across higher dimensional structures. And that Musk must have found that to sound reasonable tells you a lot about the status of the foundations of physics. But to be fair, Grok 3 turned out to be impressive indeed. It quickly outperformed all or most other AIs on a number of benchmarks, whether in mathematics, scientific reasoning, or coding. Grok excels. In the crowdsourced evaluation platform Ella Marina, Grok 3 set a new record. In this figure, you can see how quickly Grok caught up to the other models and also how much OpenAI's starting advantage has diminished. I tried Grok 3 myself. By way of reasoning, I found it to be comparable to GPT-4 and DeepSeek. A major disadvantage, though, is that you can't use both the think and the deep search mode at the same time. On the other hand, it has a big advantage over OpenAI and DeepSeek, which is that it searches ex-Twitter. Though, when I asked it to find Elon Musk's tweet about the quantum gravity Grok query, it didn't find it. Grok 3, by the way, is the first general-purpose AI model to exceed 10 to the 25 flop in training compute. This means it breaches the rather arbitrary threshold of the EU AI Act and will require additional safety tests to remain available in the EU. But America innovates faster than Europe can regulate because the law will only go into effect in August this year, and if Europe still exists by then, maybe we can agree that we've had enough safety testing already. Then, just a day after the Grok announcement, Google introduced an AI super agent, specifically designed to help scientists discover research hypotheses and topics for potential grant proposals. They call it a co-scientist, which is also what I'd call the new hire coming to replace you. The co-scientist is a super agent that supervises 6 not-so-super agents which have different roles. Like, one will come up with ideas, one will criticize them, one will modify them, one will rate them, and so on. The AI co-scientist is not yet publicly available, but Google had a few scientists try it out. One of the results has been amazing, maybe even a little scary. This came from a group which researches how bacteria evolve antimicrobial resistance. The AI co-scientist came up with a new hypothesis, which was subject of an unpublished research project of the same group, and the results confirmed the hypothesis. That is, the AI agents drew the same conclusions from the published literature as the scientists did, but did it in a few minutes rather than months. According to New Scientist, the lead author said, "We were shocked. I sent an email to Google saying, 'You have access to my computer, is that right? Because otherwise I can't believe what I'm reading here.'" So on the one hand, we have this amazingly rapid progress that isn't likely to stop anytime soon, and this has a lot of people excited. This progress will likely continue for a while. Sam Altman, the CEO of OpenAI, announced on February 12th that they plan to soon release GPT-4 4.5, swiftly followed by GPT-5 within a matter of weeks/months. On the other hand, even the more advanced large language models continue to have the same basic problems as the early ones. Grok, like all other large language models, often fails to pay attention to the exact wording of queries. In this example, it confuses 20 feathers with 20 pounds of feathers. Guess it wasn't meant to fly. It also seems to be easy to jailbreak and happily gives out bomb instructions. OpenAI's deep research tool turned out to be very good at completely inventing data tables. GPT-4o and Gemini Advanced continue to hallucinate. According to a recent study, they all invent references in the financial literature with a probability in the double digits. So, if you want bad financial advice, just stick with YouTube. And while a lot of companies have adopted some sort of AI system, the results have not been earth-shattering. In the memorable words of Edward Ackner, who does the AI integration for HSBC, much of the AI talk is a success theater.
Candidly, there's a lot of success theater out there, and we have to be very clinical in terms of what we choose to do and where we choose to do it.
And Brian Chesky, the CEO of Airbnb, said about their AI adoption, "I don't think it's flowing to a fundamental step change in productivity yet." Microsoft, meanwhile, found that AI is making us stupid, at least some of us. They tracked about 300 people in different AI tasks, such as generating content or asking for advice. They found that people fall into two camps. Those with high confidence in AI use less critical thinking, while those with higher self-confidence use more critical thinking. Then again, the idea that new technology makes us stupid is hardly new. Radio, TV, video games, the internet, Google all supposedly made us stupid. Maybe they did. The universe is an odd place, and it just became even odder, because a new analysis confirmed an anomaly that everyone ignored because they thought it'd go away. Well, it didn't. It seems that the universe looks noticeably different on one side of us than on the other. Let's have a look. This anomaly is called the hemispherical power asymmetry. It's been around since 2003, where the WMAP data showed that the cosmic microwave background has more fluctuations on one side of the universe than on the other. If that makes no sense to you, it's because it makes no sense. This asymmetry, quite simply, shouldn't be there. In fact, I don't know any good explanation for it, which is probably why physicists have largely ignored it. There isn't even a theory for it. It's just weird. The cosmic microwave background, CMB for short, is radiation that's left over from the hot plasma in the early universe, and that's now all around us. The radiation was once hot, but has since dropped to an average temperature of just about 2.7 Kelvin. However, the temperature isn't exactly the same in all directions in the sky. This is because in this hot plasma in the early universe, some places were a tiny little bit hotter and others a tiny little bit colder. So the cosmic microwave background has temperature fluctuations around the average. This is what you see in this image. The blue spots are a little colder and the red ones a little hotter. Physicists have studied these temperature fluctuations intensely because they're our best clue to what was going on after the Big Bang. Loosely speaking, they count how many patches of what size are hidden in this image. What you can see by eye is that there are a lot of patches that are kind of this size, which is about 1 degree in angular size. But really there are fluctuations of any size. It's just that they're difficult to see. If you do a data analysis and plot the sizes of fluctuations as a function of their number, then you get what's called the power spectrum of the cosmic microwave background. In this figure, the large patches are counted on the left, with a small l, and the small ones are counted towards the right. This big peak here, that's the many small sprinkles we readily see by eye. The hemispherical power asymmetry is now the observation that one side of the universe seems to have more temperature fluctuations than the other side. This is not about the CMB temperature itself, it's about the fluctuations. The CMB temperature itself is also somewhat larger in one direction than in the other, but this is because of our own motion through the universe. It's called the CMB dipole, and is more or less well understood. But the hemispherical power asymmetry is something different altogether. It means, loosely speaking, that there is more texture or detail on one side of the universe than on the other, even if the average is the same. By the way, this video comes with a quiz that lets you check how much you remember. However, 20 years ago, the data wasn't particularly good. The new paper now looked for the anomaly again in a much newer data set from the Planck mission. For their analysis, they divided up the entire sky into increasingly smaller patches and then calculated the typical size of fluctuations in them. From this, they then extracted the two directions that are most different and also calculated how different they are. There are two interesting things about this. One is that you can see in this image that in some ranges, that is for certain sizes of the patches, the discrepancy is around 3 sigma. The other interesting finding is that the direction in which the fluctuations are larger is nowhere near the CMB dipole. They find they're largest in this direction, but the CMB dipole is somewhere up here. What does this mean? For one thing, as we just saw, the statistical significance is not particularly large. Depending on how you look at it, it's somewhere between 2 and 3 sigma. That's about a 1 in a few hundred chance of something like this happening coincidentally. So it could be just coincidence. The other two options are that either the data is biased because of the way we make our observations, or our location in the universe isn't as random as it seems. Both of these options would require a major rethinking of all we know about the cosmos. Another way to think of it is that the CMB measurements are like the universe's first selfie. And like most selfies, it's showing us more details than we wanted to know. Some days it might feel like the world's going to hell, but there's a good thing about hell. It's hot down there. Maybe then it's not a coincidence that today I have good news about geothermal energy. I used to think that geothermal energy would always remain a small contributor to global energy needs. Indeed, this was my conclusion when we first talked about this some years ago. I said this because drilling is expensive, and the deeper you drill, the more expensive it gets. There are few places on Earth where the heat at moderate depth is high enough to generate substantial amounts of energy from it, and if the ground below your feet is that hot, personally, I'd stay away from it, but maybe that's just me. But wow, things have changed a lot in a few years. One indicator that I was too pessimistic is to look at the installed geothermal capacity. If it was true that drilling is just getting too expensive, you'd expect a slowdown or stagnation. You'd expect this because once the good spots have been occupied, that's it. Indeed, this is what we see with hydropower. All the good spots have been taken, and now growth has stagnated. However, the growth of geothermal electricity production has been stable for decades. Another indicator that I was too pessimistic is to look at other pessimists. Currently, the total geothermal contribution to global electricity is about 0.5%. In 2011, the International Energy Agency said that optimistically, by 2050, geothermal could reach 3.5% of global electricity production. However, in their most recent report, which just appeared in December, they write that next-generation geothermal systems could could provide up to 8% of the global electricity supply by 2050. So they've more than doubled their projection, which is quite a change. And this is only electricity production. It doesn't include directly produced heat from geothermal sources. This remarkable development has been driven by technological advances and, among other things, artificial intelligence. Yes, you have that right. Artificial intelligence can be a way to geothermal energy, quite literally. The American company Zanskar is a good example for how to make it happen. They were founded in 2022 by two geoscientists who met during an expedition in India's Zanskar region, hence the name. They're taking the scientific approach to finding geothermal sites, which can hide in unexpected places. They collect data from seismographs, acoustic imaging, gas sensors, and everything they can get their hands on. Then they throw it at a specially developed AI. Allegedly, this can reduce drilling costs by up to 66%, though it remains to be seen whether that will pan out. According to their website, even though the company just started in the United States, they have already uncovered more potential geothermal sites than the entire industry did over the prior decade. They have raised more than $40 million in funding. But AI isn't the only development that has been going on in geothermal. There are also three major trends in the power plant construction. The first is to make deeper drilling more affordable with more powerful drills. The second one is to use enhanced geothermal systems. This is a method of cracking up rocks to push water through them rather than relying on naturally occurring reservoirs. The third method is to use closed-loop systems which make the energy extraction more efficient even if the ground isn't super hot. All three methods together can vastly increase the number of potential geothermal sites. Just in the past year, multiple new startups have sprung up around those technologies and attracted significant funding. This too tells you that the outlook is becoming more optimistic, and I think it's justified. The company Fervo, which has been working on enhanced geothermal systems, reports that it's going very well, and they've just raised another $225 million. And scientific studies support the optimism. In a recent paper, a group of researchers found good news for enhanced geothermal systems. They demonstrated with laboratory experiments that it's possible to fracture hot rocks so that their permeability is up to 10 times larger than that of cooler rocks. This means that water injected into these fractures can become so hot that it becomes supercritical. This would be amazing because supercritical water can carry up to 10 times more energy and would vastly improve the efficiency of geothermal sites. Enhanced supercritical reservoirs are to geothermal energy basically what quantum gravity is to theoretical physics, except if they find it, we could actually do something with it. They say the road to hell is paved with good intentions, but maybe the road from hell is paved with geothermal power plants. So don't forget to subscribe for more hot takes. Thanks for watching. See you tomorrow.